You know, have you ever wondered how something so reliable, like the electric current charging your phone, can come from the completely chaotic random dance of trillions of electrons? I mean, how do we get predictability from pure, unadulterated randomness? Well, that's the exact mystery we're diving into today, the science of the random walk.
So, to get our heads around this, the source material uses this perfect analogy. The whole random walk problem is basically like trying to figure out where a drunkard is going to end up. Every single step is totally unpredictable. A tiny shuffle this way, a huge lurch that way, you have absolutely no idea what the next move will be. And this exact same principle applies to everything, from molecules in the air to, yes, those electrons in a wire.
And that right there, that's the big question, isn't it? It just seems impossible. If step 1 is a complete mystery, and so is step 2, how in the world can we have any certainty at all about where we'll be after step 1 million? The answer, as we're about to see, lies in the incredible power of large numbers.
Okay, so let's start at the very beginning. Let's really break down the fundamental building block of this entire process, that one single, chaotic, totally unpredictable step.
So what is a random walk officially? Well, as the slide says, it's just a path made up of a bunch of random steps. We have no clue about the next step's size or its direction. It's a total mystery. This is our starting point, pure, unadulterated chaos.
All right, but here's where things start to get really cool. Even though any single step is completely random, we can still describe the nature of that randomness. And it turns out there are a couple of key tools that let us start to get a handle on all this chaos. First up, we've got what's called the average step. You can think of this as the overall bias. Is there some kind of driving force that's pushing our walker, on average, more in one direction than another? That's what this first tool tells us.
And then there's the second piece of the puzzle, which measures the fluctuation. I love to call this the wobble. This is the pure randomness part. Are we talking about tiny, random shuffles, or are we talking about wild, unpredictable leaps? The fluctuation tells us just how big that cloud of uncertainty is for any single step.
And this slide, well, it lays it out perfectly. On the left, you've got our walker on a totally flat sidewalk. There's no reason to go left or right, so the average step is 0. It's all just random wobble. But now look at the right. Put that same person on a sloped sidewalk, and suddenly there's a driving force, gravity. They're still stumbling around randomly, but now there's a consistent downhill bias. The average step is no longer 0, and believe me, that one little difference changes everything.
Okay, so we've got a handle on the chaos of a single step. Now for the magic trick. Let's see what happens when we scale this up. I mean, way, way up.
All right, let's leave our drunkard at the bar for a minute and jump into a real-world example from physics. Inside what looks like a perfectly still copper wire, every single electron is on its own insane random walk. It's constantly crashing into the metal's atoms, bouncing off, and ricocheting in a completely new, totally random direction.
And you have to understand, the scale we're talking about here is just mind-boggling. In a single minute, one little electron takes 3 quadrillion random steps. That's a 3 with 15 zeros after it. It's an almost incomprehensible amount of chaos packed into just 60 seconds.
So check this out. With no electric field, no driving force pushing it, where does that electron end up after 3 quadrillion random steps? On average, right back where it started, 0 meters. But now apply a tiny electric field, our slope sidewalk, and over that same number of steps, the electron travels an average of 30 meters. All of a sudden, chaos has turned into a predictable, measurable journey. But here is the absolute craziest part of this whole thing. The total amount of randomness, that total wobble from all those quadrillions of collisions, is exactly the same in both scenarios. The electric field didn't get rid of the chaos, not at all. All it did was add a tiny, consistent nudge to each and every one of those steps.
And this is the number that changes everything. After that 30-meter journey, the total uncertainty, that final wobble around its destination, is just 1.64 meters. Now just think about that for a second. A 30-meter journey, born from quadrillions of random events, is predictable to within just a couple of steps. That's absolutely incredible.
So why does this happen? This chart breaks it down for us. It all comes down to relative fluctuation, how big the wobble is compared to the distance you've actually traveled. As you can see on the left, for a single step, the randomness is a staggering 3,000,000% of the average movement. It is pure chaos. But now look at the full journey on the right. The total wobble ends up being just 5.5% of the total distance. The sheer number of steps just completely drowns out the randomness.
And this incredible idea, this hero of our story, actually has a name: statistical determinism. It's this beautiful principle that says the more random events you pile on, the more predictable the overall result becomes. The chaos of the individual parts literally creates the certainty of the whole.
And look, this isn't just some weird little thing that happens inside a copper wire. This is a fundamental law of the universe. It governs processes on scales that are almost impossible to even imagine. Let's take this to a cosmic scale. Think about a single photon of light born deep in the core of our sun. Its journey to the surface is the ultimate random walk. It travels for just a centimeter before, bam, it slams into an atom. It gets absorbed, then spit back out in a completely new, random direction. And this happens 100 million times every single second.
So how long do you think this incredible journey takes? On average, 1.5 million years. A trip that should take light just 2 seconds turns into a 1.5 million year ordeal, all because of these random collisions. And yet, because of statistical determinism, we can predict that average escape time with incredible, stunning precision.
Okay, but just when you think you've got it all figured out, there's a final twist to this story. Because it turns out the randomness we've been talking about, the randomness of a coin flip or a drunkard's walk, isn't even the deepest kind of randomness that's out there.
You see, the kind of randomness we've been talking about so far, it's really just based on what we don't know. We call a coin flip random because we can't possibly track all the tiny forces acting on it. But quantum probability, that's something else entirely. It's not about us missing information. It's that the universe itself is genuinely, fundamentally uncertain at its most basic level.
I mean, how weird are we talking? Well, this quote from the source says it all. When physicists try to apply our normal, everyday rules of probability to the quantum world, they get results that are just nonsensical, like negative probabilities. That's a concept that has zero meaning in our world, and it proves we're dealing with a layer of reality that just completely shatters our intuition.
So, what this all means is the profound, reliable order we see all around us, the steady current in a light bulb, the constant light from a star, all of it is built on a foundation of randomness that is deeper and honestly far weirder than we can possibly imagine.
And that leaves us with one last really big question. This amazing principle that countless tiny random actions can create a predictable, large-scale outcome, it isn't just for physics. You see it in economics, in biology, even in sociology. So if we look closely enough at the chaos in our own world, what other hidden patterns of certainty are just sitting there, waiting for us to discover them?